So the next thing that I'm going to go over is the robot controller. So we've already gone over the view controller and the planner function, and we understand that the view controller the robot controller is part of the view controller and is created when the view appears. So the robot controller is here in the Swift, or in the set of Swift programs, and it's set up as a state machine. So it has a bunch of different states that it can be in at any point. So the stop state is well, actually, I'll go over the different where all those states are actually used. So there's the robot controller, and then there's this robot object. So the robot object is the thing that actually uses the Double SDK and instantiates or it initiates those connections, and it grabs the information from the double robot, and also it grabs information from the sensors. So the robot object basically just stores all of the data for the robot, and it also has some functions to accept actions that are given to it from the robot controller, or in some cases the override display or override GUI. So I guess I'll kind of go over what those different variables in the robot are. So this robot object is very general. It can support any robot that can have these functions and variables built into it. So ideally you could make, say, one for testing, and then you could test system behavior as it runs in a simulated environment, and then you can also use that same setup for the real robot. So the robot has this Boolean indicating a connection status. So that's used to just check to make sure that the robot is actually connected before we start controlling it. And then there's this state vars variable, and that's going to contain this robot state vars struct, and that has the x position, the y position, the angle, the battery percent, the pull height percent, and whether or not the kickstand's deployed as a number, as an integer. So that's our state vector. And then we have our state vars updated Boolean, and then that is actually going to tell us whether or not, since we last checked, there has been an update to the state variables. So that allows us to kind of just say if there's some code that's dependent on new data, we don't have to rerun that code every time. Even if there's no new data, we can wait until we get new data before running that code, and that kind of makes it more efficient than, say, running a complicated say controller every cycle. We can just only run it when we get new data. Then there's an action, which is going to be, the action is just something that you set, and let's see if I can find it. Okay, yeah, it's this. So there's this translate variable and this rotate variable, and both are floats. So this is just going to be our control, like, actuation value. It's going to say, like, how fast do you want to go forward and how fast do you want to rotate. So that is set by the robot controller, and setting it to 0 will tell it to just stay still. So that's how our control action is set. Then there's this sensors object, which is going to, it's the sensors connection object that was passed in from the view controller and created over there. And that just maintains the connection to the Linux computer and constantly queries for new data. Then there's this obstacle detected Boolean, which is going to be kind of processed from the sensor connection, the LiDAR scan. So that's just currently the obstacle detected is just 1 or 0. Is there something 6 feet in front of me and 1 foot to either side? So if there's something in that box 6 by 2 feet in front of you, directly in front of you, then it's just going to tell the robot to stop. But the robot controller manages that. So it's just a way to get very simple information from the sensors object. And then so there's 2 init functions, one without any sensors and then one with a sensors connection. This is just for backwards compatibility. Before we had that sensors connection, we didn't need this, but now we do. Then there's just some functions to do like higher level state changes. So one of the things that's kind of managed separately as part of the double system is the kickstands. So you can tell it to deploy the kickstand and retract the kickstand, and that's just a separate process from the action that it's doing. Then there's also this built-in function to turn a certain amount of degrees, but it just uses the encoder value and it's not very accurate. So we kind of replace that and just directly are sending it control actions now. But it's still there in case you want to use the Double2 built-in turn function. And then there's just this reset state variables function. And that's just going to zero out the state variables, or basically zero out, and yeah. So, like I said, this is just a very general thing. It could be used by a simulation of the robot, and as long as it has all of these methods and functions, then it will be able, or methods and variables, it will be able to be used by the robot controller. You can kind of simulate the response. So, but the actual physical implementation for our double robot is down here in this other Swift file, doublerobot.swift. So you can see this double robot object, it conforms to the robot protocol, which means it has all of those variables. This actually has a few more to implement all of those methods and all of the methods. So there's our 2 init functions, and it just sets everything to 0, and then when it's connected, it sets the connection parameter. Disconnected, it also sets the connection parameter. This is the built-in double did update function. So this thing is made by Double Robotics. It was imported from the C or Objective-C library that they gave us to control the robot. So whenever there's a status update from the encoder value, or not the encoder values, from say battery percentage, pull height, etc., it will run this function right here, and that's where we set the value indicating the state variables have been updated. And then we set so that's just those 3 things: battery, pull, kickstand. If those states change, that function runs. And then the next thing is the travel updates, which is another part of the Double SDK that was given to us. And if it moves, for example, the double object will run this function, and it will update the angle by the encoder change. So or it'll update the angle, X position, and Y position by the change in encoder value. And this was ultimately not accurate enough, just using the encoders and integrating the state change from the encoder values. It was not accurate enough to get really high quality position for even a few feet, and the angle was always pretty far off, maybe even by a few tens of degrees. So ultimately, if the sensors are connected, well, if the position sensor specifically is connected, then we just kind of ignore any sort of state changes that the Double SDK gives us, and we just rely completely on that sensor. And so yeah, in the future we could kind of, in this case, we could process and calculate those encoder updates and then send that back to the Linux computer to incorporate into the state estimate for the RealSense camera package, because the RealSense camera allows you to input encoder values and get an even more accurate state measurement. So that's where we would do something like that. So the drive should update function, it runs whenever the double needs some new instruction. So the double is operating at a certain frequency. I think it's like 10 hertz or something like that. But every time it needs new instructions, which is like 10 times per second, it'll just run this function. And it's currently programmed to just grab its current set action, the translate and rotate components of that, and just sends it into that variable drive function, which just gives it a new instruction to do every 10th of a second. So that's where the control action is actually sent to the double robot. And this kind of constrained our design because it has to be set up in a similar way to this. We can't just send it this thing whenever we want it. It will only physically use it every so often. So yeah, it's kind of detached. You set the action separately from where the robot actually reads the action. But it seems to be fast enough in all of our situations that the control system is still stable. It's not oscillating or anything like that, as long as the control actions are not too high. Yeah, so this is just kind of the logic for a deploy kickstand. It's just checking if it's deploying, then or if it's already deployed, then it's just going to do nothing. But if it's in any other state, then it's going to try to tell it to deploy the kickstand. And then this one is going to retract the kickstand. It checks if it's currently retracting or already retracted. If it is, it continues. And if it's not, then it tells it to start retracting. And then this one is just it exposes the built-in turn a certain degree function that was given in the Double2 SDK. But like I mentioned before, it was just not precise enough to execute turns of more than a few degrees. Yeah, so the last thing is this, or one of the last things, we're not there yet, is this reset state variables function, and that is just going to zero out all of our state variables. And that's what this does basically, but this is a bit more complicated because it's actually taking a coordinate transformation, and so all of this code right here is just to manage the position zeroing function that we set up. So when it's using the visual camera for for position and rotation, it's not just like we're not changing the values that are coming from the camera. That doesn't change. So what we do is we store some offset to those values, and we apply that offset before it's actually sent to the rest of the system. So this code is just to it's to store the opposite of the current value, so that when the system uses it, it can add this stored value, and then the effective angle is 0, or it's zeroed out. And in the future, when it starts moving again, this offset will be consistently added to the output. So it will always be relative angle and position from the point where you zero those values. So yeah, that's storing a coordinate transformation so that it can zero out the position and rotation. That's all you really need to understand from that. And then this is this function, ProcSensors. It's currently set up to just run this in a loop. So if you run the initialization with passing in the sensors connection, then it will run this ProcSensors function down here. And if you don't send it the sensors connection, then it never runs that. So if it has a sensors connection, it'll run this ProcSensors loop, and then that's where it actually grabs the desired format for the position and rotation, and then it actually calculates whether or not there's an obstacle in front of it in the scan data section. So this first part is just grabbing the quaternion value of actually no, that's not that. So well, yeah, okay, so this is, it grabs the position and rotation values from the camera, and after grabbing those position and rotation values, they're not in the correct coordinate frame for the double robot to use, and also the rotations in quaternion format instead of just like rotation about Z format. So the first thing we do is we grab this orientation as WXYZ, which is the quaternion format, and then we do these calculations to convert that quaternion format into Euler angles, where the rotation about Z is the component that we're actually interested in. So this heading is extracted in the correct coordinate frame from the quaternion using this function here, or this set of instructions here. And then finally, once we have that heading, we apply that offset angle. So we just take the camera's given heading, and then if there's any offset, then we add that. And by default, the offset is 0. So if you never zero the position, this offset value is just 0. And then we store that the state vars have updated, like we do if there's a double update. So the next thing we have is the position, where it's XYZ. And the Intel RealSense camera position, again, it's not in the right format. It's in a different coordinate frame, and it's also in meters. So this right here is just converting it into meters. and this negative inverts the coordinate frame to the same frame that the double uses, and then multiplying the value by 39.37, it converts meters to inches. And then we're also adding that offset value, the offset that we store whenever the zero function is run. And then finally, for position, because if there's an offset angle, you also have to rotate the position coordinate frame. This is just applying that rotation. So yeah, you invert that's just to get the angle into the right space before applying the rotation. And then we yeah, that's multiplication by the rotation matrix to change the coordinate frame into the desired direction. And then, so that takes care of updating, or it extracts the heading in the desired format and the X position and Y position in the desired format for the double robot from the Intel RealSense camera that we're using. And that's just grabbing that from the sensors connection object, which we'll go over in a little bit. So the next thing it grabs from that sensors connection object is the scan data. And the scan data is it's a bunch of distance measurements, and you have the minimum angle and the maximum angle. And yeah, so the angular distance between each direction, or between each distance measurement, is given by the formula. You take the max angle, subtract the minimum angle, and you divide it by the number of total distance measurements, and that gives you the angle change between each distance measurement. So from there we check from there we we convert each distance measurement from polar coordinates into Cartesian, and then we just have a bunch of X and Y values. So in this scan points array, so this is just an array of doubles. So you have your array of XY coordinates is the scan points. And then just to determine if an obstacle is detected, you just have you loop through these scan points and then check if X is within 6 feet, if X is greater than 6 inches, because that's the minimum distance for the sensor, and if X is less than 48 inches, or 4 feet, and Y is within -12 to 12 inches, or 1 foot on either side, so 4 feet in front and 1 foot on either side, then it's going to set its obstacle detected parameter to true. And well, actually no, this is it sets an intermediate value to true, so this is just kind of a local variable. And then to actually determine if it's a real obstacle, it averages several measurements over, or 10 measurements over time, to make sure that the obstacle reading is actually accurate and not just, say, a weird reflection or a glitch in the sensor data. So this is just taking it and making sure there's actual 10 solid measurements before you actually set, or I guess, never mind, it's 5 solid measurements before it actually sets its obstacle detection to true. And like I said, this is just to make the sensor reading a little bit more robust by double checking to make sure there really is something there before engaging the obstacle override, which will stop movement. So we found this method was pretty reliable overall for verifying the actual presence of an obstacle. So yeah, that's this robot object, the actual physical implementation for the double robot.